In this video, we present our research on markerless motion capture and introduce a model that generates accurate full-body poses from multi-view images. Markerless human motion capture is a highly demanded topic with applications in low-budget game development, healthcare, and sports analysis. Yet, despite the research advances in 3D keypoint estimation, full-body estimation remains a challenge, as the reported error in the literature for full-body pose prediction is often twice as 3D keypoint estimation. In this research, we present a markerless motion capture pipeline named SkelFormer. Our pipeline predicts the full-body pose and shape with high accuracy from multi-view images and shows great generalizability to out-of-distribution data. Our pipeline contains two stages. First, we estimate 3D keypoints using off-the-shelf models. Then we use a skeletal transformer as an inverse-kinematic model to predict the pose and shape parameters of the SMPL body model. To train our model, we use our new and improved joint regressor to create synthetic 3D keypoints from motion capture data. Specifically, during training, we use the joint regressor to convert the motion capture data to 3D keypoints that are aligned with off-the-shelf 2D pose estimators. During this process, we also corrupt the data by adding noise and occlusion to the extracted keypoints. Additionally, we diversify our training set by adding body shape and rotation augmentations. Next, we train our skeletal transformer to predict correct body parameters from the corrupted 3D keypoints. Here, we demonstrate an overview of our skeletal transformer with two novel modules. First, we use SVD symmetric orthogonalization instead of the commonly used 6-degree of freedom representations to obtain rotation matrices. Second, we use skeleton-aware attention masks on the pose decoder to restrict the attention between only neighboring joints. We show the results in several scenarios and compare it with the Deposer T, an optimization-based inverse-kinematic solution that uses multiple frames. We show the inputs with markers. Here, we show the robustness and smoothness of our model over frequent occlusions. We see that our single-frame model outperforms the temporal alternative. Next, we add Gaussian noise with a standard deviation of 10 mm, effectively adding 16 mm error on average to all of the joints. We see that our model's performance only degrades by 3 mm, while Deposer T's results drop by 20 mm. Finally, we only use 7 key points to control the pose and see that our model can correctly estimate the body with realistic movements while Deposer T fails to do so. Next, we deploy our model for markerless multi-view human pose and shape estimation. We report the performance of our model in distribution and out-of-distribution settings. Here, we show the results of our in-distribution experiments, where our model is fine-tuned on the target dataset. Our model performs best compared to prior works and has better image-body alignment than available pseudo-ground truths. Next, we perform out-of-distribution experiments in which no components of our model are trained or fine-tuned on the target dataset. Here, we show our results on videos that we collected for visual assessment. The input to the model is obtained by off-the-shelf keypoint estimators and shown with red markers. Here, we provide another sample on a small volume and see accurate results, despite the error from the 3D keypoint estimators in the hands and feet regions. We also test our approach in a larger volume and see that SkelFormer generalizes well to different camera setups. In this video, we show our results on a dancing sequence to demonstrate the realism of our approach. Despite being a single-frame approach and the noises from the 3D keypoints, SkelFormer reconstructs the correct poses with little error. Finally, we show our results on test set of the publicly available rich dataset to confirm our approach generalization and visual fidelity on outdoor recordings. In this evaluation scheme, our method performs better than other off-the-shelf human mesh recovery solutions and obtains equal results to the fully fine-tuned solutions. In conclusion, we introduce a data-driven solution for markerless human motion capture. Our method is highly robust to errors in the input data, as evident by its ability to achieve competitive results on out-of-distribution data. Our model is also over 100 times faster and performs better than optimization approaches in obtaining the inverse kinematic solution. Thank you for your time and attention.